Welcome to this explainer. I am absolutely thrilled you're here today. Think of me as your mentor for the next little while because, well, we're embarking on a pretty major transition together. You know, in your earlier studies, science was all about inviting you to just be curious, to look around and wonder, hey, how does that work? But as you step into the world of secondary science, we are totally leveling up. We aren't just looking at what we know anymore, we're diving deep into how we know it. How do we take a simple, everyday observation and turn it into a hard, concrete measurement? How do we actually test a wild idea? And honestly, how do we know when it's time to throw an idea completely out the window? You are no longer just sitting back and watching, you are becoming an active, deliberate explorer. Now, to navigate this new territory, you're going to need the right mindset, equipped with two absolutely vital mental tools. First up, the magnifying glass. This represents careful observation. It's about training your eye to catch those really subtle patterns and crucial little details that most people would just walk right past. But observation all on its own, it's not quite enough. That is exactly why we also have the compass. The compass ensures our exploration actually has some direction and purpose. It guides us to ask the right questions and, maybe more importantly, reminds us of the limits of our own ideas, because science isn't just about wandering around aimlessly. It's a highly purposeful journey to make sense of this incredible world we live in. All right, let's jump right into section 1, the art of simplification. Okay, let's dive into this. Here is the undeniable truth. The natural world is staggering, overwhelmingly complex. I mean, if you try to study every single detail of a real-world system all at the exact same time, you'll literally drive yourself crazy. It's impossible. So scientists rely on a secret superpower to solve this, the model. A model is basically a simplified way of looking at a real system. Scientists build them by deliberately, and I really want to emphasize that word, deliberately, ignoring certain details. Like when a physicist studies a moving car, they might treat that entire heavy, complicated machine as just a single tiny dot. Or an Earth scientist might treat our bumpy, mountainous planet as a perfectly smooth sphere. When we do this, we're intentionally ignoring the noise to find the signal. These choices aren't mistakes, right? They're highly strategic decisions made on purpose to keep things simple enough so we can actually find the answers we're looking for. And what's really fascinating is that this trick applies to the most complex phenomena in the universe, right up to the absolute genius level. Take the renowned physicist Meghnad Saha, for example. He wanted to understand the light coming from distant stars. Now, if he had tried to model every single atom, every microscopic movement, and all the chaotic reactions happening inside a star, no way. The math would have been literally impossible. Instead, he made a model. He simplified the whole thing, treating all that complex raging matter as just a ball of hot gas, focusing only on temperature and pressure. And by intentionally throwing out all those incredibly complex details, he achieved a massive breakthrough. He successfully explained how the color of a star is deeply mathematically connected to its temperature. Moving right along to section 2, building your first models. All right, now it's time for you to practice this new superpower with some everyday, real-world scenarios. Imagine you're hanging out watching a cricket match, and a batter just smashes the ball high into the air. Let's say we want to build a simple model to answer one core question. Will that ball cross the boundary for a 6 without hitting the ground first? When we build our model, what do we absolutely have to keep? Well, the mass of the ball, the speed it was hit at, and its direction. Those are non-negotiable. But what can we safely ignore? The brand of the bat, the color of the ball, even how tall the grass is on the field. None of that makes a bit of difference to our specific question. Even things like air resistance and the stitching on the seam can usually be dropped in a simple beginner model. By stripping away all the trivia, the core answer suddenly becomes clear. So let me put you on the spot and ask you this directly. If you were going to model the time it takes for you to ride your bicycle from your school to your house, what variables would you mentally toss out? Think about it. You definitely keep the distance of the route and your average pedaling speed, right? But you totally ignore the color of your helmet, the brand of your shoes, and probably even a tiny bump in the pavement. Actually, ignoring those details is incredibly useful because it completely stops you from getting bogged down in useless data. Which brings us to section 3, the language of science. And this brilliantly illustrates our next hurdle. All of this amazing observation and clever modeling, it's completely useless if we don't have a precise way to share it with the rest of the world. You know, in our everyday conversations, words like force or work can mean a dozen different things depending on who you're talking to. But science demands absolute clarity. To allow scientists across the globe to compare results without any confusion whatsoever, Everyday language is condensed into highly specific, shared symbols and units. So, mass becomes a simple m, velocity becomes v, force is F. It's basically a universal shorthand. It ensures everyone, no matter what language they speak at the dinner table, is on the exact same page. And to put this into perspective, this precision isn't just some boring academic exercise. It can literally be a matter of life and death. Consider a famous, real-life, mid-flight crisis involving a massive passenger airplane. The flight required exactly 22,300 kilograms of fuel to safely reach its destination. But the ground crew made a terrifying miscalculation. They used the density of the fuel in pounds per liter instead of kilograms per liter. Because they mixed up the standard units, the aircraft took off roughly 15,000 liters short of the fuel it actually needed. The plane ran out of fuel midair, literally turned into a giant glider, and they only survived by making a harrowing emergency landing. Using standard agreed-upon units everywhere avoids exactly these types of catastrophic errors. Let's expand on that and see how this builds into our understanding of equations. Look, I know math can sometimes feel super intimidating, kind of like just another hurdle of endless memorization, but I really want you to completely reframe how you look at it today. Mathematics is a language for thinking. An equation isn't just some tedious tool to make you calculate things. It is a beautifully compact, elegant statement about how different things in the universe relate to one another. Once you focus on understanding the real-world situation first and the actual quantities involved, equations stop feeling like a roadblock. Instead, they start acting like incredibly helpful guides for your own logical reasoning. All right, final stop. Section 4. Ready for the world. Okay, we've gathered our mental tools. We know how to observe closely, how to simplify reality into workable models, and how to communicate clearly using math and standard units. Now we enter the final stage, using all these skills to look ahead and predict what happens next. One of the absolute greatest strengths of science is its ability to anticipate the future under totally new conditions. But how do we separate a true scientific prediction from just a lucky guess? Let's say your friend says, "Oh, it's going to rain today," because those clouds look dark. Well, that's pretty vague, right? To make it scientific, we follow 3 key steps. Step 1, identify measurable data. We ask, okay, what is the exact humidity today? Is it above 80%? Step 2, we look at past patterns. Did the temperature drop exactly like this the last time it rained? By doing this, we move to step 3. We form a reasoned expectation based entirely on evidence. Boom, you've just completely transformed a random guess into a testable scientific hypothesis. And as you begin making these predictions out in the wild, you'll find yourself relying heavily on the awesome power of rough estimates. Let's say you want to figure out how much air you breathe in a single day. You don't need a perfectly calibrated $1 million lab to get started. You already know you take about, say, 20,000 breaths a day. If one breath fills a fraction of a party balloon, let's just call it half a liter to keep it simple, then a quick mental estimate tells you that you breathe roughly 10,000 liters of air every single day. Doing this kind of rough estimate builds your logical intuition. It instantly tells you if an answer makes sense before you ever even touch a calculator. In the real world of science, careful reasoning is often valued way more than just blindingly accurate number crunching. Which brings us to our final thought for this explainer. As you officially step into the world of secondary science, you are stepping completely out of the role of a passive student. You are now in the shoes of a real, active explorer. So the very next time you make a prediction about anything in your life, I want you to ask yourself, are you just guessing, or are you actually looking carefully through the magnifying glass of evidence? The universe is complex, for sure, but it's like a giant puzzle. It is knowable. So what will you choose to explore first? Stay curious, always trust your evidence, and happy exploring.